Okay, so thank you for the introduction, and thank the organizers for inviting me here. So yeah, as already said, I will be talking about different types of non-adiabatic dynamics and how these two types of non-adiabatic dynamics can be made to give results that can be compared. So first, let me talk a bit about my goals here. So when we are doing non-adiabatic dynamics, we are interested in electronically excited states and photochemical reactions, usually. So what we can try to do is we can take some system and we can try to predict something about it. Its spectrum, its lifetime of its states, or the quantum yields of the reaction, or any observable, we can try to predict it. Another thing that we can try with our simulations is to explain things. So we can take something that that we already know, so we take some experiment and we try to explain it. So like assigning peaks, or trying to explain a reaction mechanism in the excited states. And the last thing we are doing is improving our methods. So comparing, benchmarking, and developing them so that they are more general and easier to use. So we are always, of course, aiming for something that's black box that you can plug any system into and get results. So I won't talk today at all about trying to predict anything. So yesterday we had a very nice talk about predicting spectra for completely unknown molecules. But today I'm interested in this part, in using these simulations to explain observables. So how it usually works with my group is that an experimental group is doing a time-resolved spectroscopy of any kind, and then they see some spectra, and okay, they see the peaks, but they want to know what they are actually seeing. And this is where the theory comes in. And so it's a symbiotic relationship. So we use those spectra because if we can simulate the spectra, that means that we are on a good track, that our methods are good. And we are definitely not yet capable of saying that we can get some good results without comparing to experiment. But when we do compare to experiment, then, okay, we know our methods are good, and now we try to extract information from our simulations that explains what they are seeing in the experiment. And there are more different flavors of non-adiabatic dynamics. So you already heard a bit about these things. So I will mostly, so my area is trajectory surface hopping. So you can do full quantum dynamics, which is exact in some limits. So if you fully converge your results, you have exact solutions. You can make some smaller approximation, and then trajectory surface hopping is kind of the biggest approximation that you can make that still usually gives you correct results. So it's the lowest step on kind of the rung of these methods. So let me just very quickly say what we are doing. So we are evolving Newton's equations on a single potential energy surface. So we have the nuclei positions and we have an electronic states, and we are evolving the nuclei on the potential energy surface of those states. But since we have multiple states, other than evolving the nuclei, we are also evolving an electronic wave function, which is a linear combination of the electronic states. And we are evolving the coefficients in this equation using the time-dependent Schrödinger equation. And then, crucially, we use these coefficients to tell us when we should switch from one surface to another. So usually this is some probabilistic method that the most popular is fewer switches surface hopping, but there are other methods that tell us this. And what we need for this type of dynamics is some initial conditions, so the positions of the nuclei and their velocities and the initial states. And then we propagate, so at each step we need these gradients of the electronic states themselves, the gradient of the currently active state, and we need these couplings, which can be calculated using nonadiabatic coupling vectors, or usually it's more stable not to use the coupling vectors, but to use the overlaps of the wave functions between two steps. So this is what we need, and what we in the end get are, so first we get individual trajectories, so time evolution of the energies of the states, and at every point during those trajectories we are in one state and we change. So here we start from the fifth state, then we quickly hop to the second state, then we propagate more, then hop to the first state, and so on. And along the trajectory we can look how the geometry changes, and how we can look at the orbitals, how everything changes. And then from a bunch of trajectories, our ensemble of trajectories is basically replacing the nuclear wave packet. So we get the distribution of positions and momenta for each state, and we keep, of course, the energies. And as we are propagating, we are also always calculating these electronic wave functions, and this is where all the information on the electrons is held. But since we are usually interested in relatively larger systems than usual quantum dynamics, and we are running lots of trajectories for a long time period, we cannot save all of the information on the electronic states. So this will be, I will come back to this a bit later. But first, the main point of my talk is that, okay, yes, we have different methods for non-adiabatic dynamics, but for my current problem, the main difference between the different methods is what representation they are propagated in. So for quantum dynamics, you need to build a set of diabatic states. So these states are smooth, and you need to build them globally. So you, before running the dynamics, you need to basically build your model system, a diabatic model. And as Sandra said earlier, if you want to do it properly for some molecules, you can spend 3 years building your model before you run any proper dynamics simulations that give you results. So, but then these states are what when we talk about chemistry and photochemistry, what we are talking about are the diabatic states. So when we talk about some system, we are talking about ionic state, covalent states, for example, here, or we talk about pi star states and pi star Rydberg states. When we use those words, we are talking about diabatic states. And the second thing we have is adiabatic states. So these are the states that you get from your electronic structure on a given geometry. So they are very simple and they are well defined. So when you have your electronic structure, you calculate, you get adiabatic states. But they are not smooth. They have conical intersections, avoided crossings. And at these points, the character of the states changes completely. So when you are interpreting things, adiabatic states are not as useful. But because of this, the fact that you get them straight away, the adiabatic states are much easier to work with for the dynamics. And the main reason that surface hopping is so easy to use is that you can, in theory, just take a system and start dynamics right away. You don't need to do anything fancy. You can run dynamics, and that's why you can use surface hopping as kind of an exploratory tool, because you can start running something and get results that you didn't expect at first. And if you needed to build a diabatic state model, then even before running the dynamics, you know that you won't get anything that you didn't already put into your potential energy surfaces. So you cannot have new channels that you didn't expect. So you need to know much more about the system before. Here you don't need to know anything. Okay. But this problem that the diabatic states are useful for interpreting is so we want that in surface hopping as well, and for interpreting results, and also for benchmarking, because we want to be able to run NCTDH, and then we want to be able to run surface hopping on the same system and compare the populations. So the populations are the most basic thing that we always look at, and with surface hopping we have adiabatic populations. And with MCTDH, surprisingly, once you have the adiabatic potential energy surfaces for a single point, you can trivially get the adiabatic states. But it's hard to get back the adiabatic populations from an MCTDH calculations. So let's go the other way around. Let's try to get diabatic populations from a surface hopping calculations. So what I'm doing is basically diabatization by projection. So we take a geometry, usually the ground state minimum, and at that geometry we look at the states, we label them, giving them some diabatic labels, and then we get more geometries. They can be different minima, or usually a bunch of geometries from all the trajectories that we are running. And then for each of these geometries, we calculate the wave function overlaps between our reference structure and these other the states at the new geometry, and we get some matrix like this. And usually you get a bunch of zeros, numbers that are close to either 1 or to 0. So usually you have some reordering of the states. And this way you can easily see how the adiabatic states change over the different geometries. Okay, so just for methodology, the last slide. So what we do once we have our results, so our bunch of geometries, if we want to simulate some observable, we use the nuclear ensemble approach, and this is basically equivalent to integrating over the nuclear coordinates. We need some broadening factor, and here it's we are calculating UV spectra, so you have oscillator strength, but basically any observable can be calculated in a similar way, like averaging over all your geometries and having a broadening parameter, which is a Gaussian. And this is, so we call it nuclear ensemble approach, but this is a completely method from statistics. It's called kernel density estimation. So we use that to calculate our observables. So let me get to my examples. So first is pyrazine, which is a prototypical example of ultra-fast internal conversion. So this is a molecule where you excite to this state, and then you have population transfer to the lower states, and it's extremely fast. So we like it. We like calculating with it because it's the reaction is very fast. It has a high symmetry. This mode and this mode, these two states are coupled by a single mode, so you can easily make a very simple model. So yeah, we like it. And okay, first let's calculate the UV spectrum. So first we can calculate the line spectrum. And the line spectrum already tells you a lot. And you can already, from the line spectrum, you can already assign the peak. So you have the B2U state here, you have the B2U state here, and you have the dark AU state that does nothing here. Okay, and then let's use the nuclear ensemble approach. And we are in the adiabatic basis. So now, of course, our spectrum looks better and matches the experiment much better than the light spectrum. So even if we added some broadening to just this one point, it would be worse than our spectrum in the nuclear ensemble approach. But if we want to assign the spectrum now, we see, okay, we have the S1 state here, and we have the S2 and S3 state here. So here this was easier for assignment than this. So what we do now is use those overlaps to transform our states in the nuclear ensemble from the adiabatic to the diabatic basis. So we are projecting, and we have now this coefficient. And now we see really that this peak is almost exclusively coming from the B2U state. So we get it from the nuclear ensemble approach. We can really assign these states. And this agrees perfectly with the NCTDH calculations. So this is a spectrum that has been calculated millions of times because it's kind of a really basic example of linear Brownian coupling models. Okay, so we can do that. And then we come to this part where the different methods don't usually speak the same language. So this was a system that was studied a lot by quantum dynamics methods, and they always use the two-state model. So you have two states, and you have population, you excite to this state, and you get population into this state very quickly. So then once someone did a first surface hopping calculation, okay, they plot the populations, and they have this in the plot. The problem is that they used these diabatic state labels for adiabatic states. And then when the quantum dynamics community read this article, they said, okay, what's happening here? They have more states than we do. Let's try to make a model with more states. And Sala and co-workers made a model with more states. So these are adiabatic populations, so they are not what they are looking at in quantum dynamics. But Sala and co-workers made a model that included 4 states. They found that actually they need 3 diabatic states to explain the population as well. And they get this type of population. And now we are running surface hopping dynamics, and we are now calculating with surface hopping dynamics on the model system, we are calculating the diabatic populations. And we see that surface hopping here agrees very well with MCTDH. And the same is, we get almost the same population if we do the surface hopping calculation on a full dimensional ab initio surface. So this model potential, so surface hopping agrees with MCTDH on the model potential, and the model potential agrees with the full dimensional calculation. So we have confirmation in both directions, which is we are very happy with. Okay, then we can simulate some spectra. So we are looking at X-ray absorption spectra. I won't go into much details on this part, but we have kind of the carbon K edge and the nitrogen K edge. An experimental group did these spectra. They were looking at them. We were in collaboration with some other groups simulating the same spectra. So in these figures, it's hard to see exactly what is happening. So let's look at the lineouts. So they see some peaks, and we assign those peaks to the different states, and the red peaks are assigned to usually the B3U state, and the green peaks we are assigning to AU states. And we see that in their experiment they see these same type of oscillations that we see in the population dynamics. So we see that observables quite nicely follow the diabatic populations. And if we were plotting adiabatic populations, there wouldn't be any oscillations. Almost everything is on the S1. So this observable, it follows the electrons, and the electrons are defined by the diabatic states. So we quite nicely see the usefulness of the diabatic picture here. But we can also actually calculate the observables and make lineouts for the simulated spectra, and we see mostly quite nice agreement between theory and experiment for these things. There are some differences, but considering the difficulty of simulating this stuff, we are very happy. Okay, and one more example where this it's helpful to look at the diabatic populations and states is the ring opening isomerization of 1,3-cyclohexadiene. So it is this molecule, so it has double bonds here and here. And when you excite it to the S1 state, this bond breaks and you get a hexatriene. Okay. Again, we were collaborating with experimentalists who did the photoelectron spectrum. And so this is the experiment and this is the theory. And again, we can simulate the experiment and we are quite happy with the agreement. But then comes the explanation part. Okay, what are we actually seeing? And this is a molecule that was studied quite a bit before. And this is the usual model for this molecule. You have this B state and this A state. And we know from symmetry that dissociation has to occur on a state of, so the isomerization has to be on the state of asymmetry. So the minimum of the hexatriene has to have this symmetry. But then we look at the electron density of these states, and we see that, so the red parts are where the electrons are depleted in the excited state with respect to the ground state. And we see that in the 1b state, electrons are removed from this bond. And in the 2a state, nothing is happening at this bond. So why is this bond breaking in the state where nothing is happening on this bond? So we look at more states. And we see this 3a state, which has the correct symmetry, and where this bond is depleted, so where the electrons are leaving from here. And these two, so all three of these states are actually kind of very mixed when you look at the determinants that compose these states. And when you look at just the orbitals, they have mixed contributions that look quite similar at first. But when we do the scan with more states and try to diabatize on this scan now and project, we see that the wave function here in this region actually doesn't look anything like this state. It looks like this state. So we see that this state is going down in energy. And this is what we want when we are explaining things. So we know that there should be something happening at this bond in this state if it is responsible for the reaction. And now we see it really well. And we also see that, so when we run the dynamics and get the diabatic populations, we also see it, that this state is getting populated. But we also see that this other state, the 2A1. Oh, sorry, I have it here. So this 2A1 state is also getting populated, but that is not the reactive state. So we get some population in it, but when we are getting the hexatriene, we are in this other state. So we quite nicely see why it's important to know which state you're in. Okay, so I will finish now just to thank my group at Ruđer Bošković Institute, NAJA, Tomislav Pitesha, who did most of the work on the cyclohexadiene example. We collaborated with these experimental groups, and Piero de Cleva for the photoelectron stuff, Sonja Coriani and Henrik Koch for the X-ray absorption, and Graham and Christina for the implementation of the surface swapping into quantics. So this comparison between MCTDH and surface swapping. So thank you for your attention.
Thank you very much. Very, very nice and clear presentation. We have time for some questions.
Very nice talk, Marin. I was wondering, your diabatization scheme, is it like a binary property? So it's like if the coefficient, like the overlap with the new state and the previous one is 1, like the swap, I understand, but what if it's 0.51? And what do we do in those cases where it's not clear which state it comes from?
It's not binary, so we used, so we have this matrix that, okay, we orthogonalize it. And then basically whenever we are calculating any property, we are using that matrix as a crude adiabatic to diabatic transformation matrix. So for this type of thing, it's okay. But if we were doing it over the trajectories, if we were interested in energies over the trajectories, so if we wanted the energies of the diabatic states over the trajectories, it would be bad. But this type of, for the population, it works really well for everything that we looked at for now.
Okay, thanks, interesting.
Nice talk. I wanted to ask about the geometric phase effects, which is natural when there is a conical intersection and the dynamics takes of closed contour kind of like. So does this method handles geometric phase effects automatically, or you have to take care of it in other ways?
So the main problem of surface swapping is that it doesn't handle the coherence well, so it's over-coherent, and that ties into the geometric phase effect as well, but that's just one part of it. So basically it doesn't handle it well, but for everything, so for model systems you can often run into huge problems with surface swapping, but when you have tens of or 20 atoms, you have a lot of the phase space is very large, and these effects become smaller and smaller. So usually a very crude empirical correction to your to just handle this overcoherence problem is enough for molecules, and for model systems you can run into a lot of trouble.
Okay, any final short question? If that's not the case, let's move on and thank you.